Swayam Prabha. Digital India. Educated India.
In the previous lecture we were discussing about surface tension driven flows and their simple one dimensional mathematical representations. In the mathematical representations we started with one particular scenario in which we neglect the inertial forces or inertial effects, and then we came up with an equation. You can go to the view graph to recapitulate this, that this is the viscous force, this is the actually the surface tension driven surface tension force, but expressed in terms of the static height capital H, and this is the weight or the gravity force that is opposing the motion of the capillary. In the small time limit, when S is much less than H, then the forces which are balancing each other are the viscous forces and the surface tension forces. So, this is the viscous force. We assumed a fully developed flow to describe the viscous force, and that is balancing the surface tension force. And then we got a relationship between the capillary displacement S and the time t, where S varies as square root of the time. Now that is about the small time limit. What about the large time limit? So by large time limit what we mean, let us come to the board to explain this. So let us say that this is the capillary and this is the final static height. So small time limit means temporal regimes where the height is much less than the static height. Large time limit means the temporal regimes when the capillary front is almost near the static height. So to express the corresponding relationship, what we will do is we will write, so we will be doing now large time limit. So 8 pi mu S ds dt is equal to pi r square h rho g minus pi r square s rho g. Now let us say that what is the hallmark of a large time limit? The hallmark of a large time limit is the difference between h and s is very small. So let us say that h minus s is equal to delta s. Okay. So 8 pi mu, in place of s we can write delta s plus h, sorry, h minus delta s, h minus delta s to d dt of h minus delta s is equal to pi r square rho g into h minus s is delta s. So now one can work out this, that is h dh dt minus h d delta s dt minus delta s dh dt plus delta s d delta s dt. Clearly capital H is not a function of time, it is a static, the final static height. So this is 0, this is also 0, this being involving two small numbers will be less than the order of the other. So eventually what you get is 8 pi mu h d delta s dt is equal to minus pi r square rho g delta s. So we can write d delta s by delta s is equal to minus pi r square rho g by 8 pi mu h dt. So ln delta s is equal to minus r square rho g by 8 mu h t plus ln c1 if you integrate it. So delta s is equal to c1 into e to the power minus r square rho g t by 8 mu h. Okay. So that means we can get an expression, because once you know delta s you can find out what is h minus delta s. So that is equal to s. So we will summarize this discussion on the large time limit through the slides. So let us go to the slides there. So in the slides I mean maybe there is a different notation, instead of C1 it is C2 that is used, K2 whatever, but the form is pretty clear. So ln delta s is equal to ln C2 minus K2, K2 is that the combined term r square rho g by 8 mu h. So that in the shorthand notation is written as K2. So I mean in board whatever we mentioned as C1 that is mentioned as C2 here. So you can get s as a function of the constant C1 C2 whatever name you give. As time tends to 0 s tends to 0. So time tends to 0 has to be analyzed very carefully. In the short time limit whatever is time